Hello guys, welcome back to my channel Gamma Die Gamma. So in the previous video I believe I talked about residue calculus and how it can be useful to us and why we should even be concerned about it. In this video I'm actually going to apply residue theorem, residue calculus to evaluate some definite integrals. So let's get started. Let's start. Let's have I, which is an integral, a real integral from negative infinity to infinity of dx w of x. Well, I'm saying we can sort of solve this real integral by converting it into a contour integral in the complex plane. So sort of complexify it and make it a contour integral. And it's important to see what kind of contour we choose. Since this is a real integral, some part of the contour will be on the real axis. So a really popular choice of contour C is that of a semicircle, where you have, say, negative r and r lying on the real axis. This horizontal is the real axis, and you sort of loop around going in a sort of a clockwise direction here. Call this contour C. R is like the real integral part, the parts that are on the real axis. I'm just drawing the real axis here, and then the imaginary axis is like this. Okay. Let's write the contour integral equation for this guy. So we just have integral over r, this entire segment first, dz w of z, plus, well, this loop part, let's call this, it's denoted by this sort of arc. So the arc integral dz w of z, that is basically what the contour integral of this of around C will be. Well, what we can do for the real part, notice that we are on the real axis. That means z equals x, at least for the real part. So we have minus r to r dx w of x plus, well, nothing really on the arc part because it's not really in one axis. It's a combination of the real and the imaginary. Okay, and now if I take the limit as r goes to infinity, basically for both of these guys, notice what's going to happen. We're going to get integral from minus infinity to infinity dx w of x plus limit as r goes to infinity of this arc guy and this is still equal to the closed loop integral of dz w of z around C. Well, notice what this is. This is I. This is the guy we wanted to find, right? Now we can just set these things equal only when this guy goes to 0. So we want this guy to go to 0. So let's look at some conditions first of all that will ensure that this guy goes to 0. Okay, so in case you sort of missed this, and I might have missed it too, why are we converting a real integral into a closed loop integral? That's because if you remember the last video, we know the answer for this. This is 2 pi I times the sum of residues at the poles, or a better word is singularities, of w at z, which are inside the contour C. Since we know this, setting these two equal, we'll know what the value of this real integral is by this residue theorem formula. That's the motivation behind converting a real integral into a closed loop integral and sort of, writing a contour, complexifying it basically. Let's look at the conditions that will make this 0 now. Well, notice one thing, we can parameterize z as r times e to the I theta. You can clearly see this because it's sort of an arc centered around the origin with a radius r, and every point can be represented as r times e to the I theta, which characterizes the rotation in the complex plane. And then dz is ir e to the I theta d theta, and theta for our parameterization ranges from 0 to pi. I've chosen a semicircle because it's the most popular choice for a contour C. We may not always have a semicircle, but one thing is guaranteed: some part of the contour will be on the real axis, otherwise there will be no equality between them. They might be close, but there will be no equality unless there is some part of the contour that is on the real axis. I'm actually going to do an example where we have a rectangular contour where, of course, one entire segment is on the real axis, but instead of having this curved, it's like straight and finite. Here r is going to infinity, so although we're parameterizing it, we will be taking the limit to sort of expand this infinitely, so we'll get an infinite semicircular contour. Okay, after that was said, let's plug these things into this arc integral. Limit as r goes to infinity, 0 to pi d theta ir e to the I theta w of r e to the I theta. So closely, we want this guy to go to 0, otherwise we won't be able to set them equal. We have some part we'll also need to calculate, so this wouldn't like simplify things. So integration would not just be an exercise of finding residues, it will also be an exercise of finding what this like arc integral is, and we clearly want to avoid that, right? Why introduce another integration to avoid an integration? So to set this equal to 0, we want to do some analysis, probably what I call the essence of complex analysis. We have the absolute value of the integral of dz f of z, and we know that this is less than or equal to integral of magnitude of dz f of z. This is sort of an application of the triangle inequality, a continuous version of the triangle inequality. So what if we have the substituted guy here, the parameterized guy? We have d theta ir e to the I theta sort of take the magnitude inside and the integral outside with this inequality introduced. D theta, the magnitude of I is 1, magnitude of e to the I theta is 1, so you just have r w e to the I theta. I actually skipped a step. I should have shown that the magnitude of I r e to the I theta omega of r e to the I theta is less than or equal to magnitude of I, magnitude of r, magnitude of e to the I theta, magnitude of w r e to the I theta. And this is because of Cauchy-Schwarz inequality. We know this magnitude is 1, this magnitude is 1, we just left with r and w r e to the I theta, so that's how we have this. Now what we can do is we can sort of do another quick approximation. Well, we can say that w takes a maximum on this. We can use some theorems because we know that it's continuous, so we know it should take a maximum. These are theorems from basic calculus. While d theta will take a maximum of pi on the 0 to pi interval, so we have pi outside. limit as r goes to infinity. Well, r is like independent of theta, so take it out. So r times the w max I talked about, the maximum value that the w function will take on 0 to pi. Let me just write w max is the largest value of magnitude w of z on the interval 0 to pi. I should not include them, it's an exclusive inequality. Now it's kind of obvious that if w max shrinks faster or is comparable than 1 over r, then the arc integral will go to 0, because look what's happening in the limit over here. We are just left with r times w max. So if w max is, say, comparable to 1 over r to the n, where n is a power that's greater than 1, and we have r on top because of this, and then if you like take the limit, then we'll have a denominator that's sort of a greater power than 1, and which will clearly tend towards 0 in the limit. If it's equal to 1, we'll have something that's finite but not really 0. We want it to go to 0. So as I said, w max should shrink faster than 1 over r. So it should be 1 over r squared, 1 over r cubed, or other smaller power, or other more negative power. So this is basically the condition we have, and every time we need to check whether this condition is satisfied. This is sort of what we call the estimation lemma, which is a special case of Jordan's lemma. Jordan's lemma deals with functions which have this e to the iz part on top. So when you like substitute that in this parameterization, you get something that's a little weird, a little harder to deal with, but I have made a video on that. So although it's not in the right sequence, you can always look at that now after you know the entire mechanism for it. So although this is like mathematical jargon to you guys, I'm sure, I'm gonna do like a couple of examples where I actually show, not as elaborate as some of the questions I've done already on this playlist, but I'll try to be as clear as possible. So let's move on. Okay, let's do a simple one, sort of, which will also be useful as a sanity check. Integral from minus infinity to infinity dx over x squared plus 1. One useful thing about complexifying using contour integration is it helps us deal with these improper integrals, which bounds like infinity and negative infinity. We know from basic single variable cap, this will be inverse tangent of x evaluated negative and positive infinity, which will be pi. So we know this answer, but let's just do it by another method. Well, consider contour integral of c, then complexify this guy, dz over z squared plus 1. Well, c is now, just like the formalism I discussed before, going to be this semicircular contour. This is like the real part, negative r, and then this arc guy that we need to be careful about. And this, of course, is our popular imaginary axis, is the real axis. So that's the setup. When I write this contour integral, I'm going to have a contour integral over r dz over z squared plus 1 plus contour integral over the arc dz over z squared plus 1. Well, over r, it's on the real axis, so z is equal to x going from negative r to r dx over x squared plus 1 plus just this arc guy that we will consider shortly. And then when I take the limit everywhere as r goes to infinity, well, this guy just becomes the guy we wanted, plus this is something we need to check should go to 0. If it doesn't, it's this method or our contour choice is wrong, or this method is kind of, it won't work, because it doesn't work, you know, it's real life, shit happens. This is still equal to the closed loop integral of dz over z squared plus 1. Okay, what about this guy? Let's check for this guy now quickly. Introduce the substitution along that arc. Z is equal to r times e to the I theta, dz is I r e to the I theta d theta. 1 over z squared plus 1 will now be 1 over r squared e to the 2I theta plus 1. So, you know, this is just sort of food for thought. Now let's check in the limit. As r goes to infinity, we have absolute value integral 0 to pi I r e to the I theta d theta divided by r squared e to the I2 theta. I'm just factoring out r squared from the denominator. This of course will be less than or equal to the limit as r goes to infinity, integral from 0 to pi r d theta over r squared magnitude e to the I2 theta 1 over r squared and then this guy, if you see the limit, 1 over r squared will go to 0, so we'll just have e to the 2I theta there, and then we have r and r squared, so we just get an r in the denominator. In the limit as r goes to infinity, this will go to 0. You don't believe me, just take a piece of paper, do it yourself, pause the video. But what I'm saying is the absolute value is less than or equal to 0. This is a guarantee that the integrand inside is also 0. It's just a property of this magnitude, this absolute value. So we know for sure that the arc integral in the limit r goes to 0, r goes to infinity is 0. We know this for sure. So fine, we don't need to deal with this anymore, and we can conclude. We can quickly conclude from this that I, you know, using this equation, I is just equal to closed loop integral around c of dz over z squared plus 1. Why was there a need to actually introduce a closed loop integral? That's because we can use the residue theorem, because this is just 2 pi I times the sum of residues of poles of the function 1 over z squared plus 1 inside contour C. So let's analyze, let's look at what poles or even singularities there. If the singularity is a pole, then we need to work with poles. So z squared plus 1 in the denominator factorizes at z minus 1 and z plus 1. So we have two possible poles. So two simple poles because they have power 1. I can sort of directly conclude, I don't need to like use the multiplication limit test for this. Two simple poles. One is at I and the other is at negative I. So let's just like draw them on the diagram here. I will be a distance of 1 unit on the imaginary axis. Negative I will be the same in the negative direction. So clearly notice that I is inside the contour. So let's worry about that only. We don't really care about negative I. It's outside the contour. If you remember the tenets of the residue theorem, just need to worry about this. Since this is a simple pole, residue z equals I. Residue of a simple pole is simple, 2 pi I times, I'm just taking the 2 pi I from this over here, z goes to I, z minus I times the function which is z squared plus 1. So you factorize terms, z squared plus 1 is z minus 1 times z plus 1, stuff cancels out, you have 2 pi I, limit as z goes to I over z plus 1. So we have 2 pi I over 2I, which is pi. So this entire thing is just pi. I just checked that. This was 2 pi I times the residue, not just the residue. So this is pi. And what does this mean? Well, it clearly means that our integral I is our original integral to start with, dx over x squared plus 1 is pi, and I did this by complex analysis by using the residue theorem. You know, apart from the method that implements the inverse tangent, but such elementary functions may not be available every time as an antiderivative of this, to which you can plug into stuff. So this was one nice example, a clear-cut demonstration how to do stuff. Now let's do another example where we have to consider different contour. So let's say we have integral from negative infinity to infinity dx e to the x over 2 over 1 plus hyperbolic cosine of x. And again, I would like to convert this into a contour integral given some condition. So I complexify it and convert this into a closed loop contour integral. 1 plus hyperbolic cosine of z. Okay, well, for choosing the contour now, well, this is your integrand here. What if you're on the imaginary axis? So you parameterize as z equals 1 over z is equal to I times y. So you just get 2 to the I y over 2 divided by 2 plus e to the iy e to the negative I. I also use the definition of the hyperbolic cosine, which is e to the z plus e to the negative z over 2. If you notice that as y goes to infinity, this thing will keep oscillating infinitely. So you know it won't really go to 0. So even if we like take something that has the imaginary coefficient tending to infinity, like we have in this sort of semicircular loop arrangement that we did for the last example, since r goes to infinity, this y part eventually will go to infinity somehow, and it'll keep oscillating. It won't go to 0 on this arc. So this is a bad method to consider. I'm just doing it right now because I don't want to like waste your time by showing the steps that clearly won't work. Another thing is a pole occurs when z equals plus or minus 2n plus 1 times I pi. So for odd multiples of pi, we have a pole, because you sort of check that over here in this denominator you have, or rather in this definition, e to the odd I pi will give you a negative 1, and then a negative 1 from the other e term will give you a 0 in the denominator. So and then this since this is true for like all integers, we have infinite poles, which means that we need to do infinite residues for all the poles, because if we take like an infinite semicircle, there will be no end to, like, there will be no top to the extent that it contains. So you can just like keep adding on poles till infinity, and then our sum of residues then becomes an infinite sum. And although this is my channel, we embrace infinite sums and infinite stuff, it's not a good idea, and I don't you don't want to spend too much time on something that could have been simple, and making it harder and spending too much time on it. So I hope these reasons convince you why we need a different contour. Usually if stuff like this happens, you just choose another contour, and I will show you which contour we're gonna choose. Okay, so I'm saying let's try this contour, and this is a really genius solution. to our problem. Try a rectangular contour with a finite y, because we can't have y infinite, because it keeps oscillating otherwise. So on the imaginary axis it will become finite. So we'll call this like negative r like before, and we'll be taking the limit, don't worry about that. So we can be infinite on the x, we'll have to be infinite in fact on the x, because our real integral is indefinite in that regard, improper in that regard. Call this segment 1, and then our y here is 2 pi I. So this point here is r plus I times 2 pi. This vertical height is of 2 pi on the imaginary axis. Call this segment 2 and call this segment 3. We're going in an anti-clockwise direction. This is negative r plus I 2 pi, this point here, this corner point. So our closed loop integral around this guy is going to be limit as r goes to infinity, we need that, minus r to r on this real axis. So change all the z's to x for this r integral. So we have cosh z in the denominator, plus integral from r, now the r to r plus I 2 pi dz e to the z over 2 plus 1 over 1 plus cosh z. We need to parameterize all of these, and then from positive to negative, so r plus I 2 pi, negative r plus I 2 pi dz ez over 2 1 plus cosh z, and then the last guy, negative r plus I 2 pi to negative r dz to the z over 2 1 plus cosh z. I would like to close the curly bracket there. So for segment 1, let's parameterize it this way. Since y is the only thing that's changing, the real part is r, which will remain constant. That's our parameterization. dz is I dy. So if integral from 0 to 2 pi for segment 1, dy 2i e to the r over 2 e to the I y over 2 divided by 2 plus e to the r e to the I y plus e to the negative r e to the negative I y. So as r goes to infinity, because the limit is acting on everything in this bracket, you notice that the denominator has clearly greater powers than the numerator in terms of these exponentials. So r e to e raised to r has a bigger influence than e raised to r over 2. So the denominator dominates and we get 0 basically for this entire thing. So this thing just goes to 0. Now for part contour or part segment 2, our parameterization is z equals x plus I 2 pi. So dz is dx, and we have integral from positive r to negative r dx to e raised to x over 2 e raised to I 2 pi over 2 over 2 plus e raised to x e raised to I 2 pi plus e raised to negative x e raised to negative I 2 pi. Notice e raised to I 2 pi or any like even multiple of pi will be 1. This guy is 1. Same thing with this guy, this is 1. Well, e raised to I pi is negative 1, and that negative will flip the bounds in the correct direction. So we just have negative r to r dx 2 e raised to x over 2 divided by 2 plus e raised to x e raised to negative x, which you can sort of rewrite. Again, I'm taking the limit. I didn't write the limit for all of these for notational convenience. I'm writing the limit now because the limit was acting on this entire expression. Dx e raised to x over 2, and the denominator by the definition of the hyperbolic functions is the hyperbolic cosine, and this precisely after taking the limit is I, because this becomes negative infinity and positive infinity. So if you have I for 2. Now for 3, it's the process is not so different as 1, because dz is I dy again, and instead we have 2 pi to 0 dy 2i e to the e raised to r over 2 e raised to I y over 2 divided by 2 plus e raised to r e raised to I y e raised to negative r e raised to negative I y. And if you see, as r goes to infinity again, the e raised to r in the denominator will again dominate, making this entire thing go to 0. Doesn't matter if it's like negative 0 or positive 0, 0 is just 0. So you notice after doing all of these parameterizations, we come to the conclusion, and again I'm rewriting this closed loop integral equation. We had dz over e raised to z over 2 over 1 plus hyperbolic cosine of z. This was, well, the first guy was I, right? This first term was I, in the limit will becomes I. This goes to 0 and this goes to 0. We just calculated this, and this is I again. So I plus I is 2i, which means I is half of this contour integral. So slight correction to what we had above. Just add a factor of half. And now this is solving this is easy. This is just using residue theorem. 2 pi I times the sum of residues of singularities of the function inside contour C. That's a mouthful. Now this can get a little tricky. That's why I'm going to do it a little slowly. Okay, so well, what we have here is we have this function, and I've broken down using the definition of the hyperbolic cosine. So I can sort of write e raised to z in all positive powers by, because e raised to negative z is 1 over e to raised to z. So I can like cross multiply that. I'll have e raised to z over 2 times e raised to z, which is e raised to 3z over 2 over 2 e raised to z plus e raised to 2z plus 1. And so basically our contour integral just becomes e raised to z over 2 divided by 1 plus cosine hyperbolic cosine j dz. This, I wrote with this substitution to be 2 e raised to 3z over 2 over 2 plus 2 times e raised to z e raised to 2z plus 1. If I do a substitution where I set u to be e raised to z, I'll have this same thing. Our contour will kind of be a little different. Call it c prime. We have 2 u raised to 1/2 divided by 2u plus u squared plus 1. So we have a quadratic. You solve this sort of, or you can maybe even factorize this. In the denominator you have u plus 1 the whole thing squared, right? U squared plus 2u plus 1. So you notice the pole, it's a pole of order 2, because notice the power 2, which occurs at u equals -1. So for poles of order 2, what we need to do is we need to multiply by that thing raised to the order of the pole with the function itself, then take the first derivative with respect to that variable, and then take the limit as the variable approaches that pole. This is the residue. I hope you remember the formula for a residue of a pole of higher order. So this cancels out. Limit as u goes to negative I. Take the derivative of 2 times u raised to 1/2. So 2 over 2. U raised to, I believe, negative 3 over 2. You notice we have like a, if we take the limit, we'll have a square root of like a negative. So let's just like resubstitute, because u was, I believe, e raised to z. So we have this cancelled out, e raised to negative 3z over 2, and the limit which will go to like negative 1. But in our sort of contour that we defined before, the only thing that was inside, or if you remember, this pole occurs when we have an odd multiple of pi. The only odd multiple of pi, again, the advantage of choosing this contour was only one odd multiple of pi was there inside at z equals I pi. So we just had one pole, and that's basically what we need to substitute, because e raised to I pi is also negative 1. We're referring back to the old contour because like different, we could have we could have 3i pi, which would also, e raised to 3i pi is also negative 1. But that's why, we needed to be sure, we need to check with the contour what's going on. So you plug in I pi here, and we have as the residue e raised to negative 3 I pi over 2, which if you do your trigonometry, use Euler's formula, cosine of the angle plus I sine of the angle, you get negative I. But this is just the residue. We want 2 pi, half of 2 pi I times the residue. So I is just half of 2 pi I times the residue. The residue is negative I, we calculated that. Stuff cancels out. I times negative I is 1, so we just have pi. That is our answer for integral from minus infinity to infinity of dx e raised to x over 2 1 plus hyperbolic cosine of x. So again, we got a pi. It's a pretty nice method. Now this technique I've used of calculating residue, this may not be the best. It's actually not, may not be like the mathematically most healthy way of doing it. You could have also like taken into consideration the Taylor series, in this case the Laurent series of the hyperbolic cosine, because again you can derive it from the, like, just plug in z for in the Taylor series of the hyperbolic cosine, like we can do for the exponential functions and the circular trigonometric functions. But I don't know, I just like this method. It's kind of, I don't know, wholesome. I feel that way. So you may or may not want to stick with this method of calculating residues, because it was hard. We had exponentials. We ideally should not have treated them as polynomials by substitution, but since it's integration and since we're dealing with single valued functions, not multi-valued functions, we won't run into any troubles here necessarily. Now this method of choosing a rectangular contour, let me just give you my piece of advice or wisdom, is valid mostly when the denominator has an exponential term in it. Well, sort of the hyperbolic functions will also come in that category, because if you like expand them using the definition in terms of exponentials, you will get like an exponential expression in the denominator. That's why hyperbolic cosine came in this category. So this is my piece of observation, because the thing with exponentials like that is, you know, the poles occur infinite. There are like infinite number of poles for like each revolution, 2 pi revolution. So you just need to choose which, or sort of cancel out like the others by just closing off the top and not letting it blow up to infinity, although the real part goes to infinity because it has to. And then just trap one of them. Since the poles occur at like odd, take like the even as like an upper bound. If it were occurring at even, then you would have taken odd as like your upper bound, like I3 pi as your upper bound or something like that. So I hope you see the entire essence of this. I will probably cover a little more types in the future in the next video. I hope you enjoyed it. Yep. If you have any doubts, you can always, you know, just send comments in the comment section. Please like and subscribe to my channel, guys. Recommend me to your friends. I hope this has been insightful. Stay tuned for more content in the future, and peace out.